Today we will be talking about imaginary numbers. Okay, so these are the numbers we are familiar with so far. Natural numbers, which are 0 to 88, 67, and are all positive. Integers, which can be positive and negative, such as -4, -76, but also 300. Then we have our rational numbers, which are numbers such as -1/8, 3.67, 0.5, which are fractions and decimals. And then the little part of the rational numbers are the irrational numbers, for example, pi. And all of these numbers together are the real numbers. There are also non-real numbers, and they're called imaginary numbers. But what are imaginary numbers? They are numbers that were invented. Doesn't that sound crazy? Yes. Well, they were invented to take the roots of negative numbers. So this is how we would solve x squared is equal to 16, right? We would take the root of 16, which is 4. However, how do we solve something that looks like this? X squared is equal to -16. Well, you can, right? It looks crazy. This is why imaginary numbers were invented, to take the square root of negative numbers. To solve a problem like this one, taking the root of -16, we use I, which is the imaginary number, and it is always equal to the square root of -1. Okay, so back to the problem. We take what we already know, root of 16, and we multiply it times the root of -1. Okay, the square root of 16 is equal to 4. We know that. And we know that the root of -1 is equal to I. So 4 times I equals 4I. Here is how to solve a problem like this one. All right, so we know we'll keep the 3 times. Okay, so we'll do the same process as we did with the problem I showed you before with the -16, and we'll be simplifying this one, the -12, and we'll take out the imaginary part, which is -1, and multiplying it times 12, which is equal to 3i times square root of 12. Why is it 3i? Because this here turns into I, and so I times 3 is 3i times 12. But we won't keep the root of 12. We will simplify it further, and so we'll take it down to square root of 4 times the square root of 3, right? Because the square root of 4 times the square root of 3 is square root of 12. All right, so then we take the root of 4, which is 2, multiply it times the root of 3. We can't take the root of 3. Well, we could, but it would come out looking quite messy, and to avoid that, we'll just keep it. And then we multiply 3i times 2, which is 6i, making this our final answer. This right here is called a complex number. Why? Because it consists of an imaginary part and the real part. If you want to look at the form, it's this one right here. A plus bi. A being the real part and b times I being the imaginary part, because it's multiplied times I, so this here is imaginary. I's can also be used in exponents, such as I to the power of 8. And I to the power of 8 equals 1. Why does it equal 1? Okay, so we know that the root of -1 equals I, right? Then I squared equals -1, because -1 times the root of -1 is equal to -1. Okay, so then we have I cubed, which is equal to I squared times I, right? And I squared is -1, so it is negative, so that equals -I. I to the power of 4 equals, equals 1, because I squared times I squared is -1 times -1, right? And -1 times -1 equals 1. So now if we would do I to the power of 5, we would find out that it equals I. Why is it I? Because it would be I to the power of 4 times I, right? I to the power of 4 is 1, and I is I, so when 1 times I is I. Now if we get to I6, we will begin to notice that there's a pattern. So let me explain this. I to the power of 5 times I, right, is equal to I times I, because I to the power of 5 is I, right? And that is equal to I squared. And as we learned up here, I squared is equal to -1. Okay, now if we kept going with I7, you would begin to notice that it will be -I, and you will begin to notice that it is a pattern. I, -1, -I, 1, I, -1, -I. And this will keep going on and on. Now to I8. The problem that we were originally going to look at and that we're going to do now is equal to 1. Now you can see that after every 4, the pattern begins from the top. I, -1, I, 1. And it does the same down here, right? So I to the power of 8 would be 1, because I to the power of 4 times I to the power of 4 equals 1 times 1. And 1 times 1 is 1. Let's try a problem that looks like this. 5i to the power of 10 minus 2i to the power of 22. We would keep the 5, right? And we would focus on I to the power of 10. Now, to solve I to the power of 10, we would figure out how often 4 goes into 10. 4 goes into 10 8 times. leaving us with a remainder of 2, right? And it would be 5 times I to the power of 2i squared minus 2 times I to the power of 22. We see how often 4 goes into 22, which is 5 times, leaving us with a remainder of 2. So then we do 5 times -1 minus 2 times -1, right? Because I squared is equal to -1, as we figured out before. So 5 times -1 is equal to -5 minus -2 is equal to -3. As you can see, imaginary numbers are very useful. Without them, we could not solve the unsolvable.